Okay. Do we survive? Okay. Since we are not crashing anymore. Okay, sorry for the delay. And yeah, let's go back to this example, quite complicated, of determining the system function with a whole bunch of random property given. Okay, and so the four properties are the system is causal, and the system function is rational and only has two poles. It's equal to -2 and it's equal to 4. And also x of t equal to 1 and then y of t equal to 0. And the value of the impulse response at t equal to 0 plus is 4. Okay, and yeah, so we want to determine the system function. Then from the first two facts, we know it's unstable, but that's really not what we want to know. Okay, so I guess from the second one is the first one I want to see. So the first one I want to see is the second one. So second one says the system function is rational. So we know it's some polynomial over another polynomial. And they also told you that it only has two poles, and s equal to -2 and s equal to 4. So from just these two poles, then you know the lower polynomial must be at s plus 2 times s minus 4. Okay, and so you know that from the second equation, you know that the system function must be this some polynomial over s plus 2 and s minus 4. And because you already know where the pole is, and it's rational, it's causal, and so now you know the ROC. Okay. So the poles are at s equal to -2 and s equal to 4. And you know it's causal, and so you know the ROC must be the rightmost ROC. Okay. And yeah, so we know the system function looks like this, and you know the ROC is real part of s greater or equal to 4. Okay, and so we know the ROC and some part of this algebraic part, and then we need to use the other two things to determine this polynomial P of s here. And okay, and the third one looks really weird, and so there's a weird trick to know how it's actually used. Okay. And yeah, so you look at this x of t equal to 1 and y of t equal to 0, and you wonder how do you get h of s out of how you get information about h of s out of it. If you Laplace transform 1, then you get some weird you get a delta function thing. Okay, and that's annoying. But a way to use this is you remember back that h of s is the eigenvalue of e to the st. You remember for LTI system, e to the st, h of s are their eigenvalue, and e of st are always eigenfunction of your LTI system. And this x of t equal to 1 is actually 1 of e to the st. So it's e to the st with s equal to 0. Okay. And that means that the y of t correspond to this s equal to 0 should be h of 0 times your x of t times this x of t equal e to the x of t be e to the st with s equal to 0, and yeah, so your y of t is just h of 0. Okay. And so you see that h of 0 equal to 0. And from then you plug in s equal to 0 here, then you see that p of 0 equal to 0 here. Okay. So actually this third property is really funny, but you see that it corresponds to s equal to 0. And yeah, so you see that it corresponds to this eigenvalue equation at s equal to 0. And it tells you that p of 0 equals 0, and p of 0 equals 0, and p is a polynomial. That means that p of s has no constant term, and it has p of s is s times some polynomial q of s. Or other way to say this is p of s has a root at s equals 0. So you can factor out this root s equals 0 here with just s. And so p of s equals to s times another polynomial q of s. Okay, and finally you have this weird t equal to 0 plus condition. So t equal to 0 plus the impulse response equal to 4, and the impulse response this h of t is is the inverse Laplace transform of your system function. And so this looks like initial value of your h of t, and indeed it's h of t. And yeah, so we can use initial value theorem. And this is also where, okay, and so to use 4, remember we also need 1. Okay? Because for the initial value theorem, it says that you can only use the initial value theorem if your system, if your function is 0 for t is 0, but system is causal, so it means the h of t starts from t equals 0, so it's nice. So h of t is causal, so it starts from 0, and we know that 0 plus is 4, so it's 4 and something here. So t and h of t. And the initial value theorem says that the initial value is the s go to infinity value of this h times h of s. And now we have h of s here, and p of s is now s times q of s, so we have this s squared q of s over s squared minus 2s minus 4. S go to infinity, this is equal to 4. And now we know q of s is polynomial s, and so this thing, and but when s goes to infinity, this thing goes to constant. That means the numerator order of numerator must equal to the order of denominator. And but you have already s squared here and s squared here, and so q of s can only be a constant term, because if it's higher order term, then s goes to infinity, this goes to infinity. So q of s is only a constant, and it's really easy to read that q of s equal to 4 here, because yeah, because 4 and the s squared cancel s squared here. Okay. And yeah, so your h of s is 4s over s plus 2 divided s plus 2 times s minus 4. And with the RC, we already said RC is real part of s greater than 4. Okay, so that's derivation about h of s from some seemingly random conditions. Any question? Not. Then let's go to the next topic before unilateral Laplace transform. Okay, so it's about how to write block diagram, and I want to go pretty fast here because this is something you can learn in other classes. But I will give you some basic about how to analyze this block diagram with system functions. So we've seen a bit of those block diagrams in chapter 1 and chapter 2. But now we see that we can solve them more easily with the system function. So if you do Laplace transform on everything, then we see that we can write the relationship more easily. Okay. So for example, we have those interconnections, this parallel interconnection and this series combination or interconnection, and then from just the basic properties of Laplace transform, we see that if we have a parallel interconnection, and here we are assuming everything is LTI, so you have this applying this system is just convolute with H1, and it means that you are multiplying some big H1, some multiplying big H1 on time domain. And anyway, so for the parallel interconnection, we have that the impulse response of this whole system is you adding those two things together, because you apply this one, and then together. And then by linearity, so you do Laplace transform on both sides. You see that the system function for this whole thing is just the system function for the upper thing plus the system function for the lower thing. And similarly for this zero interconnection, we know that, and this is what we derive in chapter 2, we see the impulse response of the whole thing is the impulse response of the first thing convoluted with the impulse response of the second thing. And now if we take the Laplace transform, then we have this very nice equation. We see the system function of the whole thing is just the system function of the first thing times the system function of the second thing. Okay, and we can also analyze the feedback system like this quite easily with some algebraic on our system function of different wires. So assume we have this weird feedback system where we have XOT inside and then go through this editor actually addition but actually minus sign on here. So you kind of go through this thing and then go through some system 1 and it's split and the feedback goes through the system 2 and subtract your thing here. Okay, so you have this weird feedback loop here. And we will learn more analysis about these systems in other classes, but now we can do some equation on system function of them. Okay. And the equation on system function of them says that, okay, so you just look at the different connections and to see how different the system function, to see how the Laplace transform of different wires relate to each other. Okay. So we have XOT here, and we say go through this editor, and this addition here, it becomes EOT, and this feedback is ZOT, and the output thing is Y of T. So all those three parts are Y of T because it's a copy here. And so big Y is big H1 times E of S. This is because this H1 connecting E with Y. And Y is E goes through H1, so big Y is just H1 times E. And then similarly, you have Z equal to H2 times Y. Because this is Y, this is Y, this is also Y. And then we have this weird addition here. It says that E equal to X minus Z, because you have plus here and minus here. Okay, so we have those three things, and we want a system function. We want to relate Y with X, so we want to eliminate those intermediate E and Z. Okay, okay, and then we arrive at Y of S equal to so we eliminate one by one. So Y of S equal to H1. So H1 is just a constant, H2 is just another constant, kind of. H1 is just some function of S. And E of S, you become X of S minus Z of S. And Z of S, you substitute by this H2 and Y again. So now you have Y of S is just H1 of S times X of S minus H2 of S, Y of S. And then you move things around and then you divide Y of S by X of S. Then you see that the system function of this weird feedback interconnection is H1 of S divided by 1 plus H1 of S, H2 of S. Okay. And yeah, so you see that you put whatever system here and you can get this very nice closed form expression about what happens if you put system here and what is the system function for this whole feedback interconnection. Any questions so far? Okay, and let's go back to an example that forgot. I think we also go through very quickly, but I think we did this. Okay. So we go through this integrator example in chapter 2. Okay, so this is like an instantiation of this thing. So we have this thing now with H1 being 1 over S and H2 being 3. Okay, and so this thing we will have that H of S just is H1 being 1 over S, H2 equals 3. So 1 over S plus 3 is 1 over S plus S over 3. Okay, and so H of S is so you multiply by S on both the upper part and lower part. So H of S is 1 over S plus 3 here. And then we can further write down a differential equation. So in differential equation, we talk about how to write the system function for differential equation. But obviously, you can also convert differential system function back to differential equation. So we see that this system, so this feedback loop corresponds to this differential equation that's dy dt plus 3y, because this s corresponds to dy dt, and this 3 corresponds to 3y equal to xot. So yeah, and then we can kind of go. So you see, we can kind of go back and forth between differential equation and this feedback loop block diagram. So this is a way to design systems that give you system correspond to some differential equation. Okay. So although in this example we go from block diagram to differential equation, but as we're going to see next, we are going to show how to define go from differential equation go to block diagram. And but this example, just as a small reminder, is an example that we also do in chapter 2, and so we design is a similar thing in chapter 2. But when we do that, we were thinking about integrators and such. We were saying that xot equal to y of t equal to some integration with xot, etc. And that check out. So in chapter 2, we actually have this diagram. It's -3 here and plus sign here. And we remember this 1 over s correspond to h of t equal to u of t. So this you have this h of s equal to 1 over s here. And you remember if you do inverse Laplace transform back, that corresponds to h of t equal to u of t, and that corresponds to an integrator here. So that was the integrator feedback loop design we had for this differential equation, and we see that we can derive it kind of a bit easier by looking at the system functions, the Laplace transforms. Okay, and let's see next example. This is also okay. This is well a bit of what we say, but it's more intermediate. And now we are going to show. So here we have a block diagram, and we solve for the system function. And in this example, we say that we are given a system function, and we ask you to give a block diagram. Okay, and we are going to see that given a system function, there are a lot of ways to give a block diagram. And so a very stupid way to do this is you think about the system function. So this is s plus 2 over s plus 3 as 1 over s plus 2 times s plus 1 over s plus 3 times s plus 2. And we already know how to do 1 over s plus 3 is this thing. So you have 1 over s plus 3 here. And then we see that this is some h1 times h2. And so you can just serial connect with another system function, another system that give you s plus 2 here. Okay. And yeah, so this is one way to do a block diagram for the system function. But just like kind of what we talked about in chapter 2, we don't like this positive power of s here because it actually corresponds to a differentiator. And differentiators are, because this s corresponds to a differentiator, and the differentiator are hard to compute, hard to design. They are not very stable. Okay, so we try to get another block diagram that don't have this s plus 2 component here. And to do this, we think about how the y here is related to this z here. Okay, so we want our output y of t equal to s plus 2 times 0 z here. And yeah, and I think we can skip a little bit of the middle part. But so what we see here is y, we want big Y equal to s plus 2 times z. And and the hard part is get sz here. But we already see here, so you just look at this part here. So this is okay. This is really small, but it's 1 over s. And this 1 over s here means that the relation between e and z is kind of what we want. We already have that z equal to. So from this thing we have z equal to 1 over s times e, right? big Z equal to 1 over S times big E, and that means big E is just equal to S times Z. Okay. And so big Y is, and so from here we just have big Y equal to E plus 2Z. Okay. And so let's skip all the going back to differential equation thing, and we see that we want Y equal to this Z here is 1 over S plus 2. So this block here already give us, from previous example, this block already give us big Z equal to 1 over S plus 3 times big X. And then we want Y equal to S plus Z, then we can just take the E out here. We see that Y equal to E plus 2Z here, and so we can have this more complicated interconnection give our system function, because this thing will have our Y equal to 2E plus 2Z. So you have multiplied by 2 here, and adding this extra E wire here. Okay, and yeah, so this function gives us this block diagram, gives us this system function of S plus 2 over S plus 3. Any question? It's quite complicated. So yeah, and here is back to time domain analysis, but basically same as this frequency domain analysis. Okay, and here are some reminder to you, saying that if you want to multiply by S, that corresponding to you do a differentiation, and but differentiator hard to do. We like this multiplication of 1 over S because it corresponds to doing integration, and the integrators are easier to implement in real world. Okay. And the next example, we have a more complicated example. So we have h of s is 1 over s plus 2 times s, 1 over s plus 1 times s plus 2, and if you multiply it out, it also equal to 1 over s squared plus 3s plus 2. Okay, and then we can, so we can also write the differential equation about this thing. I think we don't really need to go back to this, okay, but I guess let's go to this. Okay, and so this corresponds to differential equation. Okay, so in this form, you see that it corresponds to a differential equation. You can read here, d squared y dt squared plus 3 dy dt plus 2 dy equal to x of t. And so just similar to the previous example, you can rewrite the differential equation to this direct form block diagram. Okay, and let's try to verify here. So dy dt squared, so let's move this thing around, move things around here. So what we have is so we move everything except this to the right hand side. So d squared y dt squared equal to x of t minus 3y dy dt minus 2y of t. And that'll be same as this this diagram here, because then we write e and f here, and so we have f will be dy dt, and e will be df dt equal to d squared y dt squared, because it's the integrator, and the reverse is differentiation and differentiation. So e of t equal to d squared y dt squared, and f of t equal to dy dt. And we want e of t yeah, and so in time domain, this just says e of t equal to minus 3ft, so this is 3f of t here, and minus 2y of t, and plus x of t, and this is satisfied here. So e of t equal to x of t plus is minus 3 times f of t. So minus 3 f of t, once again, is minus 3 times dy dt, and minus 2 times y of t. Okay. So this is a direct form of writing down this equation. You can multiply all this denominator, and you write down the differential equation in a bar diagram in this form, the direct form. And then there is also cascade form and parallel form. So cascade form is that you basically you need to do some algebraic manipulation on your on your rational function, and I guess these are all for rational function. These diagrams are all for systems correspond to differential equations, so they have rational h of s, and the rational h of s here. So here we are just multiply everything on the down step, and it will give you direct form. And for the next form is cascade form, so you basically write it in this root factorization. So you write h of s is 1 over s plus 1 times s plus 2. And so you just have a system for 1 over s plus 1 and another system for 1 over s plus 2. And already know a similar system, so we'll write it down just here. So s plus 1 here, so it's minus 1 here, and s plus 2 here, so it's minus 2 here. And finally, we can also do partial fraction expansion to write this 1 over s plus 1, s plus 2 as 1 over s plus 1 minus 1 over s plus 2. And so we will have this parallel interconnection. So we have a 1 over s plus 1 system and 1 over s plus 2 system here, and you do a subtraction here. Okay. And finally, we have a more complicated example here. We have h of s is 2s squared plus, so now it's a fully rational function. H of s equal to 2s squared plus 4s minus 6 over s squared plus 3s plus 2. Okay? And you can factor it into this funny form. So 1 over, so the numerator times the denominator. So denominator, you can just write a direct form like this here. And numerator, once again, you can get a bunch of differentiator, but it will be unstable. But instead of having an unstable thing, you can get a 2s squared. You can get a s squared from here and 4s from here. And then minus 6 over the previous output from the next one. And so we just had 2s squared plus 4s and minus 6 of everything. So this lower part is different, is 1 over s squared plus s, 3s plus 2. And the upper part, you have those three things here. And so this is a direct form to have a rational function. And yeah. And any question? Otherwise, this is the end of our. We have two things. Okay, this is the direct form of the bar diagram, and you can think about the cascade form and the parallel form by writing this kind of partial fraction expansion and kind of writing in these factors and partial fraction expansion. Although the partial fraction expansion is a bit funnier because you have 2 here. And yeah. Okay. Any question? If not, we have extra time, and let's try to talk a little bit about. I guess we'll talk a little bit and maybe still stop early, but this is quite mouthful, and let's see this a little bit. Okay. And the next topic of this chapter is the unilateral Laplace transform. Okay, and this is a very nice concept because it can help us to solve linear differential equation with initial values. And initial value problems are actually not UTI system, but they are very useful in all kind of physics or engineering. And let's go to unilateral Laplace transform. Okay. So what is unilateral Laplace transform is, well, it's defined here. is another transform that's very similar to Laplace transform. So see you have this integration, also XOT u2 minus STDT. So it's still a transform from XOT to some function. Here write is as I guess is big X of S. So it's still this transform between function of t, time, and function of frequency. But the only difference is that in Laplace transform, integrate from minus infinity. But for unilateral Laplace transform, it's only on one side. It means that on the left side we cut off. So the integration is from 0 minus. Okay. And this minus sign means that if you have some singularity at t equals 0, we also include it. Okay. And yeah, so I guess this is so a bit of notation. So our notation is kind of funny. So we say XOT unilateral Laplace transform to this script big X of S. Okay, but it's really mouthful. So I guess in the talking we'll still say it's big X of S. Yeah. But when you look at the text, you can know this is a unilateral Laplace transform because it's curvy here. Okay. And we also write this as a UL of XOT. So it's a unilateral Laplace transform of XOT. Okay. Okay. And unilateral Laplace transform, they are nice and for solving differential equation, and they are also very different from Laplace transform. Okay. And I guess I lose a lot of information about Laplace transform because first of all you start with t minus t at 0, so obviously you lose a lot of information about XOT. And also because you start integrating from t equals to 0, there is the RC of unilateral Laplace transform is totally decided because it only because this integration only depends on the t greater than 0 part of XOT, and that means RC is always a rightmost half plane. So you actually don't need to specify RC for unilateral Laplace transform. That's very different from very different from the Laplace transform we talked about. We'll be talking about Laplace transform of you need to pick the correct RC, etc., etc. But for unilateral Laplace transform, the RC is always the rightmost one because of this cutoff at 0 minus. And then the inverse unilateral Laplace transform is going to be very similar to the bilateral Laplace transform, but you just pick the RC being the rightmost one. I guess let's see some example of unilateral Laplace transform. Okay, and first we consider this really weird signal. X of t equal to t to the sum power, t to the n minus 1 over n minus 1 to the factorial e to the minus at u of t. And this is a really weird signal, but we see that you have a u of t here. So x of t equal to 0 for t is less than 0. So when you try to apply this formula to do the integration, you see this integration is the same for either unilateral Laplace transform or bilateral Laplace transform. And that means that the unilateral Laplace transform is a bilateral Laplace transform, and we actually have this in the table. Is this 1 over s plus a to the nth power. This is a thing that they use to do the inverse Laplace transform for your rational functions. And then you have the 2 to the n minus 1 because you take this, you take x of s equal to 1 over s plus a, and then you do a differentiation, you get a whole bunch of t power here. And yeah, so this is the algebraic part. So this is just same as the bilateral Laplace transform. And the bilateral Laplace transform will be this 1 over, the algebraic part will be this 1 over s plus a to the nth power. And the RC will be, as we say, it will be the rightmost one because it's a right-sided function. And RC is you pick the right side. RC is the real part of s greater than minus a. Okay. And okay, so this is an easy example of unilateral Laplace transform. And now let's see a funny example of unilateral Laplace transform. You have this x of t equal to e to the, so it's very similar to this one. but this is our favorite function, but shift a little bit. So x over t is e to the minus a t plus 1 u of t plus 1. And we think about this as well. Let's think about a greater than 0. So it's easier, it's a decaying function. It will be more convergent. Okay. So a is greater than 0, then the function looks like this. And well, it's basically our favorite e to the minus a t u of t, but time shift to a minus 1. Okay, so you have a t plus 1 here. Okay. And bilateral Laplace transform we can do by time shift and can get by our favorite example in the time shift, and we'll also see this in another example today. Okay. So bilateral Laplace transform will be this x of s equal to e to the s over s plus a, and the real part of s greater than minus a. So it's RC is this greater than minus a, and x of s is this 1 over s plus a, but this time shift give you a try e to the s vector. Okay. And now what about the unilateral Laplace transform? And the unilateral Laplace transform is going to be different from bilateral Laplace transform because the integration only starts from t equal to 0. And so integration only starts from t equal to 0, so all this minus 1 to 0 part is going to get cut off. And so if you do the integration carefully, then you see this big x of s equal to integration from 0 to infinity, and this thing e to the minus a t plus 1 and u of t plus 1 e to the minus st, and let's see carefully. Okay, so you have e to the minus a and times 1, so e to the minus a here, and u of t plus 1 doesn't do anything because it's already cut off a higher u of t, and so you have e to the minus st times e to the minus at, so e to the minus t times s plus a and dt. And you do the integration, so e to the minus a is just a constant, you get extra e to the minus a here, and is e to the minus t s plus a. Integration by t, you get this 1 over s plus a factor, and at infinity equal to 0, at 0 equal to 1, so you have extra 1 over s plus a factor. Okay. And so this is e to the minus a 1 over s plus a with the real part of s greater than minus a. So the RC is the same. RC is still the right part of this point minus a. But you see you have e to the minus a here, but you have e to the s here, and they are different. Those are different functions of s. This is e to the s, this is e to the minus a. Okay, and yeah, so we see the bilateral Laplace transform and the unilateral Laplace transform are different. Okay, and yeah, and we also see that the x of s is actually the bilateral Laplace transform of not the x of t but x of t u of t, because you are integration from t equals 0, so it's really the same as you are integrating of x of t u of t. Yeah. And yeah, so that's the unilateral Laplace transform. And okay, we want to. I guess we can stop early today here. And yeah, but so this is some very easy example of unilateral Laplace transform, and for now we know this definition is here. It's a Laplace transform, but with integration from t equal to 0 minus, and the R, because it will be right-sided, and the RC will always be the rightmost RC. Okay, and so that's if there is no question, let's stop a little early today, and let's continue on next Tuesday on unilateral Laplace transforms. Okay, so yeah, see you on next Tuesday. 对啊，S 等于0就是我们有这里用的其实是另外一个 function，这里用的是我想想看，这东西，我突然忘了，这个是怎么写的？哦，是这样写的吧？e2的，要怎么弄提出来？对，所以我们是说 e2的 st 会变成 h of s2的 st，这件事情。然后这个是 x of t，这个是 y of t。对，那我们发现，那我们 take x to take x equals 0的话，那 x equals 0，那我们就回到 h of t 乘以1。
所以它跟这个东西没有任何
对啊，不太有关系，就是，对啊，它其实是用的是这个东西。
那这个方程式是从
这个是第3章来的。
它这个是指的是说 x，然后都会 raise
没有，这个没有，这个是很久很久以前我们在第3章的时候说过，任何的有 t，任何的有 LTI system，然后任何的 e2st 都是 eigenfunction。我可以翻一下吗？等一下。